Okay, here we are back again. This is one of the optional topics from one of the later chapters in the textbook. Not really sure why I'm doing this, but I think it's kind of interesting, and maybe you should see some interesting things in mathematics without having to always do a problem set to go along with it. But at any rate, mathematical induction is a method of proof, and it helps us prove, especially theorems in number theory. Um, Interesting. Um, I'm just going to go through it real quick. There are some problems that are on Blackboard. Um, you can take a look at them if you want, but I'm just going to give you a brief introduction to this. You can think of it as the falling domino principle. If you have a bunch of dominoes, and I'm sure you've seen these demonstrations in the past, where you they're stacked up in crazy patterns, and you push over the first one, and then all of a sudden, first one knocks over the second one knocks over the third one knocks over the fourth one, so forth and so on. And what happens is an entire beautiful pattern is continued on and on. Well, that's mathematical induction. And it basically says if the first domino falls and every falling domino causes the next domino to fall, then all the dominoes will fall. So that's mathematical induction. And that's a method of proof. It's usually proven in proving theorems in algebra, which state relations which are true for all positive integers, and it consists of two steps. Step one, prove the proposition is true in case n equals 1, which basically means the first domino goes over. And step two, prove that if the proposition is true in the kth case, then it must necessarily be true for the k plus first case. This is known as the inductive step. In other words, step one means first domino goes. Step two means whenever a domino goes, it makes the next one after it go. Okay, so if that happens, um, then all the dominoes go. They all fall, and that's proof by induction. So do a simple example, and let's do Gauss's rule. So Gauss's rule is a rule which says if you want to add the numbers from 1 to n, 1 plus 2 plus 3 plus 4, dot, 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 that you get n times n plus 1 over 2. And we did this in arithmetic progressions, and we wrote it a little bit differently. We wrote it as n times a plus l, where a was the first term, l is the last term, over 2. Same thing. Okay? So, known as Gauss's rules. I'm just going to go through it quick, and you know it's true. And this is the rule that we wrote down forwards, wrote down backwards, added them up. Each column adds to the same thing. So you have n columns, each column adds to n plus 1, but we added it twice, you got to divide by 2. So that was Gauss's rule. Okay? So step one, the first domino falls. Well, if you put in, if you're adding the numbers from 1 to 1, obviously the sum is 1. If you put a 1 in here, you get 1 times 2 over 2 is 1. So step 1 is verified. Step 2 says if this is true, which is the kth case, then if you add an additional, called the k plus 1 case, you should get the same thing you got here, except k is replaced by k plus 1. So if k is replaced by k plus 1, this becomes k plus 1. And if k is replaced by k plus 1, you get k plus 1 plus 1, or k plus 2. So our goal is to show, we assume this is true because that's part of the if, and we want to show that that implies this is true. So that's our goal. All right, so basically it's just algebra. Here's the sum of the first k. We're adding k plus 1. This we know is k times k plus 1 over 2. That's our premise, our if part. And we're adding k plus 1, and we want to show that that turns out to be this expression. So there's some algebra involved. So here we go. We're adding fractions, and this has a denominator of 2. We want this to have a denominator of 2, because you can only add like terms, and common denominator that's really like terms. So we put a 2 here and a 2 here, and you work this out. You get k squared plus k, 2k plus 2, ends up with k squared plus 3k plus 2, fact at the top, and lo and behold, we get what we were looking for. So that's the proof, an alternate proof of Gauss's rule, adding the integers from the consecutive integers from 1 to n. Okay? And there are some interesting ones too. I mean, you know, you can look at this. So what are we doing here? It says proved by mathematical induction. This is a half. This is a sixth. This is a 12th. Yada yada yada. That should add up to this expression. Okay. So I guess I'll go through it quick as long as we're here. But I think what would have been better, I probably should have written out what these terms are. Okay. But I think if you write things out, then you tend to see patterns. Okay, so at any rate, step 1, n equals 1k. So plug in a 1. The first term really, you get 1 over 1 times 2 over a half, and you put in a 1 here, and that's a half. So that seems to be work. So now, we're going to apply the inductive step, which says, in English again, if the kth case is true, the kth domino falls, it implies the one after it falls. So I imply the k plus first case. So here's the kth case, which we assume is true. And then we add the next term. And the next term, well, this is our goal. The next term would look like this. I'm replacing k by k plus 1. So this becomes k plus 1. K plus 1 becomes k plus 2. And we want to show that we get you know, this expression where k is replaced by k plus 1, we want to get this expression. So let's see what happens. Here's the assumption, right? This is the kth case. We're adding this expression, and this, we're assuming this is k over k plus 1, so we're assuming the kth case is true. Here's the k plus first term, and we want to show that we do indeed get this expression. So it's just algebra again, okay? So again, it's adding fractions, you want LCD, so clearly the LCD is k plus 1 times k plus 2 in parens. So therefore, I'm multiplying top and bottom here by k plus 2. And now I have a common denominator, so I keep the bottom and I work the top. So k squared plus 2k plus 1. And that, of course, works out to k plus 1 times k plus 1. These guys cancel, and you know, lo and behold, we get our expression that we're looking for. Okay, so there's all sorts of things that you can do with this. It's very cool. Okay, what I would like to show you is this topic I call perils of inductive reasoning. So let's minimize this one, maximize this one. Okay, so perils of inductive reasoning. Now, inductive reasoning is kind of reasoning that goes from particular to general. So you find a whole bunch of cases where a proposition is true, and you say, well, gee, I hope and wonder and that if the general conclusion is true. That's inductive reasoning. Most of the time, what you learn in high school geometry is deductive reasoning. You start from a bunch of general ideas and you apply them to a particular instance. So we're going from general to particular. This is going the other way. And inductive reasoning can be fraught with perils. So I just wanted to look at a few of those just to give you an idea of what the idea of proof is. Okay? And, you know, just in general, we tend to do a lot of proofs of math. We did a lot of proofs, especially in the trigonometric areas in this course. And I don't think many people like proofs, but sometimes they can be useful. For example, Gauss's rule, the way we prove that, we wrote the sum once, and we wrote it a second time backwards and added up, and we noted some things, and that proof really had some really great features to it, and we used it again and again in various circumstances. So that was a proof that was really useful. It gave us a wonderful method. Another type of proof, which you'd only see if you took Calc 2, is when you go to solve something called the first order linear differential equation. It's this nasty looking formula And yeah, I've taught the course many times, and I don't really have it in my brain. But what I do know is I do know how the proof went. And it turns out, instead of memorizing the crazy formula, if you simply follow the steps in the proof, it's a wonderful method, and you get the results you want without any memorization, just by doing common sense and knowing a few of the basic steps. So that's another example, along with Gauss's rule, of a proof that's often taught, which actually is a very useful method. So I'm going to talk a little bit about proofs in general, but at any rate, let's get back to this idea of inductive reasoning, where we go from particular, in other words, individual observations that appear to be true, and then we want to reach a general conclusion. So, classic example one. Is there a formula for generating prime numbers? And one expression which has been offered in the past is n squared minus n plus 1 plus 41. And that seems to generate primes. So let's see, if n is a 1, what do you get? You get 1 minus 1 plus 41. Prime, yes. 2. 2 squared is 4 minus 2 is 2. 2 and 41, 43. Is that a prime? Yes. 3. 3 squared is 9. 9 minus 3 is 6. 41 and 6, 47. Is that a prime? Yes. Try one more. N equals 4. 16 minus 4 is 12. 12 and 41, 53. Is that a prime? Yes. So his 4 instances, when we plug in is 1, 2, 3, 4, and you get a prime. So that would make you think, hey, maybe this thing does generate primes. Is that a coincidence? Or so we're going from particular or individual cases, and we're trying to reach a general conclusion. Does this expression generate a prime? And well, let's see. I mean, if well, I was going to use a silly example of a person lying to you. If they lie to you once, all right, you know, maybe it's an accident. Lie to you a second time, a third time, a fourth time. At what point do you stop believing them altogether? I mean, so this kind of thing, inductive reasoning, going from particular to general, you know, we come across this. So it turns out, all right, let me shrink this down a wee bit. It turns out n equals 1, 2, 3, 4, 5, up to 15 generates primes. Up to 30 generates primes. Up to 40 it generates primes. But, alas, at 41 it fails to generate a prime. So here's a situation. This is kind of amazing in mathematics, that the first 40 instances turn out to be, or to support, or hope, let's say, that we get a prime number, that this expression n squared minus n plus 41 is a prime number generator. So it brings us, and yet 41 is clearly not, because 41 squared minus 41 plus 41 is just 41 squared. So clearly 41 squared is 41 times 41 is not a prime, right? And you can try this for some other values which are indicated here in red. This is on blackboard. So we have 40 consecutive incidences where this expression generates a prime, and yet that's not enough. So proofs are important, okay? So even things that occur many, many, many times, they may not be generally true, okay? So we have to be very careful when we look at a bunch of situations that appear to be supportive of our general aspiration or hope, and see if it's really true. That's why this is called perils of inductive reasoning. Okay, so let's do another one. Now this is another classic. There are pitfalls. Now here's the plan. There are pitfalls associated with inductive reasoning. All right, so we have to be careful. Classic example number 2. Maximum number of regions formed when chords are constructed in a circle. Okay, so no chords, 1 region. 1 chord, 2 regions numbered 1 and 2. 3 chords, 4 regions. 4 chords, 8 regions, 5 chords, 16 regions. So at this point, you're probably looking at this and you're saying, well, gee, 1, 2, 4, 8, 16. See, if you keep a chart here where the number of points, number of regions, so I'm taking points on the circumference of a circle, right? 1 point, 2 points, 3 points, 4 points, 5 points, and I draw all the possible chords, right? Number of regions formed. Well, if you take a look at well, these numbers are obvious. I'm just increasing by 1, right? So that's clearly a pretty easy pattern. The number of regions formed, though, if you take a look at these numbers, 1, 2, 4, 8, 16, what do they look like to you? Well, doubling, doubling, doubling. They're powers of 2. So you would guess if you have 6 points arranged around the circumference of a circle, you'd get, well, you'd think 32. If you had 7 points, you'd guess, well, double that again, 64 regions. So, actually, that doesn't work. All right, so we have 5 instances where, you know, visual common sense would say that's a nice pattern. You would get 32 here and 64 here, and yet that's not true. All right, you only get 31 regions if you have 6 points, and with 7 points you get 57. And it turns out that this idea of powers of 2, this sequence here for number of regions, is actually busted. And it turns out to be this expression. And, you know, so I actually prove this later on. I'm not going to go through the proof, but there it is, okay? So there are perils associated. By the way, the proof is really cool. You should take a look at it. It's very well done and illustrated here. It uses combinations, which is something that we worked on in the past with counting methods. So you should take a look at this. But I just want to warn you, when a whole lot of things seem to happen, it's very dangerous sometimes to go from the particular instances and try and assert that a general conclusion is true. Okay, so let's go on to Goldbach's conjecture. Okay, this is rather cool. What I really always liked about this is this is the kind of mathematics that I could explain to a 4th or 5th or 6th grader, and they would understand it. And this is something that has puzzled mathematicians, I don't know, for almost 300 years. So let me tell you a little bit about it. I think it's interesting, and it's one of the reasons why I really love mathematics. All right. Goldbach's conjecture states that every even counting number greater than 2, in other words, talking about 4, 6, 8, 10, 12, 14, 16, yada, 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 is equal to the sum of 2 prime numbers, often in more than one way. Now, how did this come about? The Russian mathematician Christian Goldbach first proposed this conjecture. A conjecture is something we think is true, but we haven't proven it, in a letter to Leonard Euler in 1742. Euler is one of the greatest mathematicians of all time. He's ranked up there with Isaac Newton, who developed calculus, given credit for that, and Gauss. So Leonard Euler is probably one of the top 2 or 3 mathematicians who ever lived. And back in that day, 1742, they didn't have iPhones, they didn't have calculators, they didn't have telephones, so they were the mathematicians at that point would write back and forth to one another and often challenge one another to look at a proof they had done and disprove it or find a better way or even challenge them. And this was what happened here. So it's called Goldbach's Conjecture, 1742. And it turns out one of the oldest and best known conjectures in number theory in all of mathematics. And well, if you take a look, if you go back to, which one did we do here? Is this the one? It's not quite what I was looking for. I probably closed it out. Oh yeah, well here, we looked at this situation and it tested true for 40 instances if n squared minus n plus 41 generated a prime. And that's kind of amazing, but I don't want to do that yet. Okay, but with Goldbach, this has been tested up to 4 times 10 to the 18th. So that's a 4 followed by 18 zeros. Most of us will probably have billions and billions and billions and billions. Remains unproven, despite the fact it's been verified up to this incredible number. So a couple examples, just to give you an idea. 6 can be written as 3 plus 3 in one way. 20 can be written in several ways. 3 plus 17, 7 plus 13, right? The sum of two primes. 50 can be written in 1, 2, 3, 4 ways. That 3 and 47, 7 and 43, 13, 37, 19, 31. 50 can be written as the sum of two primes in 4 ways. 100 can be written in 6 ways. Generally, and a lot of research has been done about this, as n increases, the number of Goldbach decompositions, I'm calling it, increases, but there are exceptions. So 100 can be written in 6 ways, 128 in only 3 ways, the sum of these 3 pairs of primes. So that's something to think about. Okay, so I'm just letting you know this has been proven, demonstrated true by the method of computer up to 4 times 10 to the 18th, and yet it's not true. We don't know for sure. It might be true. We think it's true. It seems to work, but we don't know for sure. So one of the reasons why mathematicians are, I'm not going to say in love with proofs, but we use proofs to check our reasoning. Okay. And one last thing I'd like to show you, one of the greatest proofs ever. You've heard of this guy, Euclid. Over 2,300 years ago, circa means about 300 BC. So over 2,300 years ago, Euclid proved there are an infinite number of primes. And this is an alternate method of proof. This is called a proof by contradiction. So we had inductive proof. I showed you a little while ago in geometry in high school. We learned the proof by deduction, when you start with general rules which you know are true, and you apply them to propositions, that, statement proof type thing. So this is another type of proof called a proof by contradiction. So the theorem is there are an infinite number of primes. So Euclid, amazing, 2,300 years ago, made the assumption that there are a finite number of primes, let's say n of them, where n is a finite counting number, and he wanted to prove that that couldn't be so. So if he proved that his assumption is false, then it would mean there are an infinite number of primes. That's called a proof by contradiction. All right, it's like the contrapositive you learned in logic. Okay, so here we go. Define the n primes in a finite list to be P1, P2, P3 up to P sub n, and construct some number P, P sub 1 times P sub 2 times P sub 3, yada yada yada, times P sub n plus 1. So, in other words, Euclid assumes there are n primes, a finite number, whatever n might be. And he multiplies these guys and adds 1, and he calls that number P. And he goes to examine P. And he says, which is true, P is either prime or it ain't. It's not prime. If P is a prime, then P is a prime that was not on our list. Therefore, our assumption was false, that there are a finite number of primes, therefore infinite number and our theorem is proven. So that's sort of trivial. If P is not prime, then it must be divisible by some one of our primes in our prime list, because these are the only primes, if you assume that, right? That's known as the prime factorization theorem. Okay, so let's notice that P cannot be divisible by any of our primes, because you'd always get a remainder of 1. We'll go in a whole number of times with a remainder of 1. That's why he added the 1. Since there would be a remainder of 1 upon division by any of these primes, therefore our prime list is incomplete, i.e. our assumption is false. In either case, our original list was incomplete, our assumption is false, therefore the number of primes is infinite. So that's a cool introduction to a very, very famous theorem by a very famous mathematician 2,300 years ago, a proof by contradiction. Read this a few times, see if you can get it into your head, but it's one of the most beautiful proofs ever written. It's much shorter than this. I sort of wrote a lot of English in here, but it's much shorter than this, but it's so cool. Okay, so I don't know, I'm hoping I gave you some insight into proof. Mathematicians love proof. We feel comfortable when we can prove things. Sometimes even propositions which we really believe are true may not be, or are not proven. Okay, so let me end here, and hope this was helpful to you, enjoyable maybe. I guess if you like math, you probably like this. If you didn't like math, you're saying, well, what's the point? But that's what we like to do. So be well, and hope Calculus 2 helped, Pre-Calc 2 helped you out a bit.